All right, let's jump right in. We're going to explore the incredible world of bone tissue engineering. And really, this is a field that's at the absolute cutting edge of medicine, where scientists are literally building the future of healing, one tiny porous scaffold at a time.
Our bodies have this amazing innate ability to heal. You break a bone, and it knows what to do. But there are limits. When you have a really severe trauma or maybe a disease that leaves a gap in a bone that's just too big, the body's natural repair crew, well, it gets overwhelmed. This is what doctors call a critical size defect. And that's where the real challenge begins.
For decades, the go-to solution has been a bone graft, which often means taking a piece of bone from the patient's own hip. But let's be honest, this gold standard is far from perfect. It means a whole second surgery site, which brings with it risks of chronic pain, infection, and of course, you only have so much spare bone to give. All of this has created a huge clinical need for something better. And that something better is the engineered scaffold. Now, this isn't just some simple passive implant. It's a sophisticated temporary structure that is designed to work with your body.
The key term we have to get our heads around is biomimetic scaffold. Biomimetic, it's a bit of a mouthful, but it just means it mimics life. Specifically, it's designed to imitate the natural scaffolding inside our bones. The really critical words here are porous, which lets cells and nutrients get inside, and biodegradable, which means it's designed to just fade away once its job is done.
So how does this actually work? Well, think of it like a major construction project. The scaffold, that's the temporary framework you put up for a new building. Then, the body's own bone-forming cells, the osteoblasts, they're the construction crew. They move in, they use that scaffold as a blueprint to build the new tissue, and once the new structure can support itself, the original framework just dissolves away, leaving nothing but new, perfectly healed bone. Okay, so this sounds amazing, right? But designing the perfect scaffold is a massive challenge. It's an incredibly delicate balancing act, a whole series of trade-offs that engineers have to navigate to get everything just right. And at the absolute heart of this dilemma is a fundamental trade-off. On the one hand, you need high porosity, lots of little holes and open spaces, so your cells can move in and get all the nutrients they need. But just like a sponge, a super porous structure is usually mechanically weak. If you make it too dense, sure, it's a lot stronger, but then you risk choking off the very cells you're trying to help. Finding that sweet spot is the name of the game. This chart really shows just how far we've come in this game. Over on the left, that's the strength of your natural spongy bone. You can see how some of the earlier scaffolds were just too weak. But then look at the bar on the right. These advanced GS scaffolds can now be tuned to perfectly match the strength of real bone. That is an amazing feat of material science. But here's the paradox, and it's a big one. You actually can't make the scaffold too strong. If the implant is way stiffer than the bone around it, it ends up taking all the mechanical load. This is called stress shielding. Your bones need stress to stay healthy. It's that whole use it or lose it principle. If the scaffold shields the bone from that stress, the body basically says, hey, I guess I'm not needed here, and starts to dissolve the very bone you're trying to grow. So, to solve this incredible balancing act, the materials themselves have gone on this amazing evolutionary journey. It all started with simple, natural polymers. Then came stronger, more controllable synthetic polyesters. The third wave added bioceramics, which made the scaffolds way more inviting to cells. And now we're in the age of advanced composites and even bio-inks that can be 3D printed and can release medicine right at the injury site.
And it's not just what it's made of, it's how it's built. The architecture is everything. Thanks to advanced 3D printing methods, we can now design these scaffolds with mind-blowing precision. We can create things like gyroid structures with these beautiful, smooth surfaces that are perfect for fluid flow, or super strong diamond lattices for heavy-duty support. We can even spin nanoscale fibers that almost perfectly mimic the body's own matrix. The point is, the structure can be tailored for the exact job it needs to do.
Okay, let's make this super concrete. Let's look at a case study. Iron is very strong, but on its own, it degrades too slowly and isn't very friendly to bone cells. So researchers had an idea. What if we mix it with hydroxyapatite, or HA, which is the natural mineral found in our bones? They started experimenting with different recipes, as you can see here, trying to find that perfect mix. And what they discovered was a classic Goldilocks scenario. Too little HA, and it didn't really help. Too much HA, and the whole thing became brittle. But right at 10% HA, they hit the sweet spot. The scaffold was strong, it degraded at a much better rate, and it was way more inviting to bone cells. It's the perfect example of how you can tune these materials to get the best of all worlds. So we have a material, we have a design, it all looks great on paper. But how do we prove that it will actually work inside the human body? Well, that's where a whole series of rigorous tests comes into play. I mean, this is the million-dollar question, isn't it? It's one thing to design a scaffold on a computer screen. It's a whole other thing to confirm that living, breathing cells will actually treat this thing like a home, a place where they can not only survive, but thrive and get to work building new bone. So before it gets anywhere near a living creature, every single scaffold has to run what I like to call an in vitro gauntlet in the lab. First up, do cells even stick to the surface? Then, are those cells staying alive? Special dyes will light them up, green for live, red for dead. Next, are the cells actually changing into bone builders? There are chemical tests for that. And finally, the ultimate proof. Does a special stain detect new calcium deposits? Because that's the hallmark of new bone.
And the results you see are often just stunning. For many of these modern biomaterials, you get over 95% cell viability, even after several days in the lab. That's a huge confirmation that these materials aren't toxic and are actually providing a really hospitable environment for those cells. Okay, but now for the ultimate test, putting the scaffold into a living model. In these studies, often done in rabbits, researchers can literally watch the healing process happen over time. At 4 weeks, you can see new bones starting to creep in from the edges. By 8 weeks, it's really starting to integrate into the scaffold's pores. And by 16 weeks, the results can be just remarkable. The defect is fully bridged with new, healthy bone. It's amazing. So this brings us to the really big picture. Because this isn't just about finding a better way to fix broken bones. This represents a fundamental shift in how we think about healing itself. This quote from the research team led by R.T. Mushtaq really sums it all up perfectly. It's about finding that promising balance to not just improve surgical outcomes, but to actually accelerate how quickly a patient can recover. So ultimately, the big idea here, the main takeaway, is this massive shift in medicine. We are moving away from a philosophy of just replacement, of just plugging a hole with a piece of metal or plastic, and we're moving towards a philosophy of regeneration. These aren't just implants. They're intelligent, dynamic structures that team up with the body, empowering it to heal itself more effectively than ever before. And that leaves us with a fascinating final thought to chew on. Bone is an incredibly complex, living tissue, and we are right on the verge of being able to engineer it on demand. So, if we can master this, what comes next? Could these same principles, biomimetic scaffolds, cell guidance, controlled degradation, could they one day let us build not just tissues, but entire functional organs? The possibilities are just extraordinary.